Okay, sound testing. Hopefully it works. Right. Testing. Okay, it's about time, so let me get started, as always. So, hello everybody, this is Junichiro Horikawa, and this is the weekly Houdini tutorial live that I'm doing, and this is the 27th episode for the tutorial live. And today's topic is to create this kind of soap form, what looks like a balloon maybe, using just the SOP based node or method without using any dynamic simulations like DOPS. And what you can do here, let me show you what you be able to create by following the tutorial today. So this is one example, starting from a sphere, then set some constraining edge on top of the sphere. Then you can either inflate the geometry without affecting those constrained edges, or you can also try the shrinking simulations as well by clicking this shrink toggle. In that case, the geometry goes inside like a soap form, like creating a minimal surface. For that, maybe I could make a little bit less constrained edges and see how it goes. So something like this. So this kind of simulations, I'm going to do it based on a geometrical operations, just by using some geometric operations together with some useful Houdini nodes. Right. And by changing some shapes, you could also create some interesting geometries, like by toggling some of the, by changing some of the parameters, you can create some kind of grape-like shapes. Let me show you how it looks like. Let's see how this goes. Okay, gotta turn off the shrink. Yeah, something like this. You can also exaggerate this by speeding up simulations. Yeah, like this, without using any dynamics. So I hope you find this interesting, and please try to follow if you would like to know how it's been done. Although you could also download the file of this project file that I've created previously from a description page on a YouTube video page. So if you like to see the project file, if you like to download it and use it for yourself, you can go to the YouTube page to download it, and it's free to use as always. Right, so let me get started from scratch. I'm gonna create a new project file, and then let me just set up some display settings. Go into the background and make it dark so that I can see it a little bit better. Okay, now shall we start? Okay. Hi, hello. Thanks for the comment as well. So I'm a beginner on programming and I'm studying architecture. Do you recommend Grasshopper or Houdini for a start? If you're a beginner on programming, I think starting from Grasshopper is a good idea, since it's a bit easier than Houdini in terms of creating geometry. So, and when you are comfortable using Grasshopper, then going into a Houdini is a good idea, I think, since you can do a lot of mesh-related operations with Houdini, but not the nerves. So if you are into your nerves, then you have to stick with Grasshopper, I think. Alright, let me create a geometry node first. Then let's start by creating a base geometry. It could be any kind of geometry, I think. It could be torus, could be cube, could be like a big head. But to make it simple, I'm gonna start with the sphere. Then let's set the quality or density or resolution of the sphere a bit higher than usual, since you want to move each vertex by some rules. So I'm gonna set the frequency to 30 so that I have enough points to make it make kind of a dynamic shape. Alright, so now I have 9,000 points. Let me save this file to somewhere so that I don't lose the process. Okay, let me name this SORP surface. Okay. Now, next thing I want to do is to create some kind of constraint edges on top of this sphere. To make it simple, I'm just going to cut this sphere with a random angle using some grid or something, and then use that, use the intersected curve as a constraint edge for this time. But the edge could be anything you want, so you could also create some Voronoi based curves or just draw your own curve on top of this geometry. That should also work for you. Okay, I'm going to make a null first and connect with the sphere. I'm gonna name this base. Right. It says, is it related to electrons, orbital shapes? I don't think so. It's nothing related to electrons. Right. Okay, and let's make a grid. And let's make a grid that is big enough to cover all the sphere. So, and I'm going to set the rows and columns to 2 and 2 so that I don't have any unnecessary edges for the grid on top of the grid. So I think the default size is big enough to cover the sphere, so that's good. Now, next thing I would like to do is to rotate this plane randomly in 3 dimension, then use it to create a intersected seams with this sphere. So to do that, I am just going to do a for each number, then give some random numbers how many constraint edges you want, say 4. Then connect the grid to the for each begin. Then I'm also going to create another node. I'm gonna name this controller so that in order to have all the parameters that I want to control later on. So I'm gonna store all the parameters in order to change the shape. And the first parameter that I'm gonna set is number of edges. With the integer type. Let's say starting from 1, the maximum to 10 for now. Right. Okay, copy this parameter, then go back to the for each end, paste relative reference. Now you can have a loop with 3 iterations. Okay, now next thing I wanna do is rotate this plane randomly on 3 dimension. So I'm gonna use a transform and make some random value for x, y, and z rotation value right here. And to make all the iterations random, I have to change the random seed for each iterations, for each rotations, also for X, Y, and Z. So first I'm going to create a global random seed. Going back to the parameter, the controller null node, then create a float number. I'm gonna name this random seed, say edge random seed. Right, then set the range probably from 0 to 100, then set the value to random, copy this, then go back to the transform. Then first of all, I'm going to just paste what I have just copied. So paste relative reference gives you a expression which links to a edge random seed that I've just created, this one. And what I want to do is to use this value as a random seed value, and the value itself should be different for each iterations, for each loop iterations. And in order to make each iteration different, one way is to use a detail attribute from this for each count. If you go to the for each count and then show up some geometry spreadsheet, at the detail you have this value called iteration. And starting from 0, if the total iteration number is 3, which is written here as well, then for each iterations you have 0, 1, 2. So we can use this value to differentiate the random seed value for each transform node at each iterations. So to access that, I'm going to first say multiply by detail of for each count, and I want to access to the iteration attribute at 0 position. Okay, so this should give you a value from 0 to 0, 1, 2 at each iterations. Okay, now I also would like to make each X, Y, and Z value different based on this one, so I'm just going to multiply the whole value by some constant random value that you set by yourself. And maybe I could, instead of multiplying the edge random seed with the iteration value, maybe I could just say plus. Okay, now I'm going to, so this will be the random seed, and in order to create a actual random value, I have to use a expression function like rand. Okay, and as a result you'll get a value between 0 to 1. So finally, after you have gotten the 0 to 1 value, you can multiply it by 360 degrees to have a random value between 0 to 360. Alright, so this is for the X. I can copy this and then paste it for Y and Z. To differentiate, you just have to change the value that right here to some other random values, other constant random values. Could be any value. Right, so this should give you X, Y, and Z a different value like these for each iteration as well. And as a result, you should get 3 different randomly rotated plane. And if you increase the iterations right here, you have something like this. Now, by having this, I want to calculate the intersection with this geometry, with this sphere. So let's just do that by using a boolean like this. And then the first input could be just solid or surface. Then the second one could also be just the surface, and then just want to get the seam, so check seam. And I don't need the AA seam or BB seam, I just need a AB seam like this. So yeah, that looks good. And I think the number of iteration edges a bit too much, so I'm gonna reduce it to 3 for now, like this. And if I change random seed right here, you can kind of have a variation of edges. Maybe try it 4. Alright, looks good. So this is going to be the constrained edge in order to stick, in order to fix the point which is close to this sphere. So the point which is on the sphere, which is close to this constrained edge, wouldn't move, will be fixed, and other point that is a bit far from these constrained edges will be moved inside, either inside or outside, using some operations that I'm going to show you on the next step. Okay, so in order to determine how you would determine which point should be fixed or which point should be flexible, going to create one point wrangle to apply some attributes on top of each point on the sphere. Okay, so the first input for the point wrangle should be a sphere itself. Then the second input will be this constrained edge. Use it as a guide, which point should be fixed, constrained. Okay, so let's name this constraint. And open up the code editor. And let's write some code where to fix the point. Okay, so first of all, you need to determine the distance from each point on the sphere to a closest point on a constrained edge. So for example, for this point on the sphere, the closest point on the edge is somewhere around here, right? And for this point is right here. And for this point, probably this point is the closest point on the edge. And what you want to do is to calculate the distance between these 2 points, then use that distance value to evaluate whether the point on a surface on a sphere should be fixed or not, depending on how far it is from the edge. So to get the minimum distance between points and edges, first I am going to use a function for vex called x, y, z dist, right? And we are checking the edges which is coming to the second input. So the first parameter for x, y, z distance is 1. Then I'm checking with the current point position, so I'm going to set at p for the second parameter, like this. Right, so as a result, you should be able to get a distance value for each point. Now the next thing is to first of all, let me apply this or promote this attribute or distance value to the dist attribute to check the minimum and maximum. Okay, so go to the spreadsheet, geometry spreadsheet, to the point tab. You'll have a new dist attribute, and the minimum seems to be really close to 0 and the maximum is around 0.5. So obviously the distance that is close to 0 should be fixed because it is kind of on top of the edge. The point is on top of the edge. But the distance that is far from these 0, like 0.5, shouldn't be fixed, should be really flexible enough. So by checking it maybe until 0.01 or 0.05 is a good number to fix. Not sure. Maybe you want to also precisely change that with some parameters. So let's create some parameters in order to control the range. In what range do you want to fix the point? So, and you can give a maximum, minimum, maximum for that range thing. So first I'm going to create a parameter called minimum, also a maximum, and this is equal to a minimum distance from a point to edge and maximum distance from point to edge. Right, so let's promote this by clicking here. I forgot to say semicolon here. Okay, so let's just set it to random value for now. Then I'm going to use these value minimum maximum to clump this distance out, meaning I'm going to update the distance value using a clump function, which you can cut the value minimum and maximum using these two values. So the value that I want to clump is distance, and I can use minimum maximum value created from a parameter to clump the value. By using clump, you can cut off, like for example, if the minimum is 0.15, then if the distance have value that is less than 0.15, then all the value will be raised up to 0.15. And same for a maximum. If the distance value have a value more than 0.6, then all the value will be reduced to 0.6, which is more if the value is more than 0.6. And after I have clumped it, I also want to use the fit to remap this value between 0 to 1, because that is easy to use with. So something like this. Okay, maybe you could also use fit 0, 1 or something, but I'm getting used to using this one, so you have to mention that. All right, now I should be able to have a distance value modified using clamp method and fit function, and let's check that out by setting it as a new attribute. Okay, so I have a bunch of zeros, and I don't have 1 because maybe the maximum is too big. So let's make it something like this. Okay, now and I am going to use this value as a weight value in order to determine which point should be fixed and which point should be flexible enough to move. So to make it understandable, I'm gonna name the attribute for this distance as weight. Okay, so if the weight is 0, then the point should not move. If the weight value is equal to 0 or close to if the weight value is close to 1, then the point should be flexible enough to move. Let's try to check that by using the color node. So I'm going to connect the color and set the option for the color type to ram from attribute, set it to weight, then set the 0 value to red, set the 1 value to blue, like this. So red means is that the point should be fixed and shouldn't move, and the blue means it should be flexible enough. Now currently the red part looks a bit too much. There's too much point that should not move, so maybe I can reduce the value for this minimum value, like this, to make the range a bit smaller. Maybe I could try with 0.03, and maybe I could also reduce this maximum value as well. Like this. Okay. How's this for now? Yeah, I could try with this. Now this is just to check which point is fixed, which point is not fixed, right? You don't really need to have this if you are sure what you're doing, but just in case. Okay, next thing I am going to currently, if you look at the point attribute, there is no more attribute, so I am going to add a normal node to add a normal attribute for the point, like this, so that I can have a normal directional value attached to each point, and I'm gonna use that normal value in order to move the face outward or inward later on. Okay, so now's the time to actually calculate the simulations, do the simulations. All the preparation has been done right here. So to create the simulations, my favorite solver, right? Let's do this. Connect the solver network, then get it into it by double clicking it. Okay. Now, first thing you would like to do is to, based on the weight value together with some speed that you're going to specify by yourself, how fast you want to move, I am going to move each point to outward, meaning to the normal direction, by some value. So I'm gonna do that using a point wrangle. I have a comment saying, how long did it take you to get good at Houdini? Well, I don't believe I'm that good at Houdini, but in terms of effects, it took me around 2 years to get used to, I think. Okay, so I'm going to name the first point wrangle as an offset, and it will be, the code that I'm going to write is a very simple one, just one line in order to move the point outward or inward based on the speed and a weight value, which is already stored in each point. So at P, since I want to move the P value, point position value, first I'm going to use a N at N, which is equal to a normal value, a normal vector value at each point. Then I'm going to multiply it by some custom speed that you specify yourself, and also multiply it with a weight float attribute that you have applied. So if the weight value is 0, then no matter how much value you have on speed, the value is still 0 because you multiply with 0. If the weight is equal to 1, then the point could move, so the speed can be used 100%. Alright, apply, accept, then promote the speed value. Let's stop with really small value like 0.1 or something. Now it's already changing something. Maybe that's too much. Let's set to 0.05. Right, and let's see how it looks like by going out of the solver, and then if I play it. Now the the point has been moved and some of the edges is stuck or stopped or fixed, so these are the places where the weight value is equal to 0, and the point that is moving outward is the place where the weight value is not equal to 0, more than 0. And as you can see, some of the points is not on the same radius as these values, so that is where the weight value is close to in between 0 to 1, so like 0.5. Maybe these points should be weight equal to 0.5, maybe these are weight equal to 0.75 or something like that. Okay, but obviously enough, the current result is not natural enough, so we have to kind of define a bit more stuff inside the solver. So go back to the solver, and next thing I would like to do is to after I have move the point outward, what I want to do is to smoothen out the result, meaning doing some smooth operations to this geometry. So to do that, there is mainly two ways using a Houdini node, I think. One is to use a smooth node, one way is to use a attribute blur. And this time I am going to use this attribute blur because what's good about this attribute blur is that you can kind of apply a weight attribute right here. So, and as we already did, we already have an attribute called weight on each point. So we can directly use that attribute for this weight attribute, and this weight attribute will reduce how much blur you want to apply to each point. So if the weight attribute is equal to 0, then the no blurring will be applied using this attribute blur. But for the smooth, there's no options to do that. You just have a constraint points, which is to completely fix the points. But that's not really what we want. We want to gradually fix the point based on the weight value. So this is using attribute blur is a bit better way to do that. So let's connect attribute blur with the point wrangle. Then set the weight attribute to weight like this. And I don't think we need to check this pinboard point. Maybe we could keep this as it is, since this geometry is a solid geometry. There is no open edge. If you have an open edge, maybe you want to uncheck this, probably. Right, and you also want to set the value, this blurring iterations, how many iterations you want to have for the blurring. More you have, more smooth value, more smooth results you'll get. And as you can see, by setting a value to really high value, you still get these constraint edge fixed, because we have set the weight value attribute as like this. So if the weight attribute is equal to 0, then even though you have a really high iteration value, you still have these points fixed at its point position. So already you are seeing some kind of SORP based form, minimal surface like form. Right, so maybe you already got the idea how it works. So this is kind of an important node in this tutorial in order to create a SORP surface. But since I want to make it as an animation as well, I don't want to make it too big. I want to iteratively increase the value, increase the blurring value. So it started with really low value, like 5. And this value should also be parameterized so that I can later control this value to see the difference of the result. So go back to the geometry node, network, going back to the controller. I'm going to add another parameter called a blur iteration. range from 0 to say 50. Starting with 5, copy this value, then go back to the subsolver again, paste it right here. Okay, so is it 5? Yeah. Right. Now, after I have offset the point outward, then doing the blur, what I want to do next is to update the normal direction, because currently the normal direction is derived from the sphere, but after we have modified the geometry, the actual normal direction has been changed. You see that this blue line is not actually perpendicular to this surface anymore. So we need to update that for the next iterations for the subsolver. So to update it, we just need to connect the new normal for the point. And now the perpendicular normal direction has been updated based on the current geometrical shape. So before it looks like this, now it looks like this. So for a next time step, the point should move based on this blue line towards this blue line. And this setup will make the simulations a bit natural than just dealing with the normal that is derived from the sphere. Okay. Now, honestly, this is pretty much it for this simple setup. We need to do some more in order to make it a bit more realistic, but at least the basic setup has already been done. If you try to play it, you already have some good looking result that I already like. But as you can see, more timeline you go, the geometry starts to go inward like this. And if you look this with some ghost shaded view, do we have that like wireframe? We have some self-intersected geometry like this, and starting to go inward and inward like this, and that doesn't look really realistic, honestly. When the geometry comes like this, and when they start to have a self-intersection like here, then honestly I want those geometry to stop growing. But because there's no constraint between the self-geometry and between self-geometry, this geometrical modification just get going, and I don't really like that, so I want to add a little bit of additional setup in order to restrict, in order to have some kind of it's kind of a fake, but kind of have a self-intersected collision. Okay, so let's think about how we could do that. Going back to the subsolver, what we can do, maybe I can explain in a sketch. So currently we start from a sphere, then the sphere is growing outward like this, and at some point the sphere has an intersected part like this. So whenever it happens, or whenever it starts to happen, I want to stop these points that is inside the intersection, the self-intersection, to stop moving, to make it fixed. These points. So let's think about how we could do that. Okay. So if we look carefully at this intersected place, let's think about it in geometrical analysis way. So first, the value that we already have is a normal direction for each point, like this. Right? And let's think about the point which is inside this self-intersected geometry, and how we could determine if that the point is inside the geometry or not, if the point is inside or outside. Now I have tried several ways to try out which one should work, and I found that there is one characteristic for each point that is inside a point, which is different to those point out on the outside, is that if we cast a ray at a point from inside, say right here, from right here. So first you want to cast a ray perpendicular to this point to both ways, right here. And if you found an intersection for both casting, for both rays, so currently if this point has casted a ray to perpendicular to both direction, then if you found this point and this point intersected, meaning if you found more than two intersected points, then this means that this point could have a really high possibility that is inside the geometry as a self-intersected point. If we check the point outside with the same method, say right here, then do the ray casting on both perpendicular direction, this direction could intersect with a other side of the surface right here. But for this ray casting, for this ray, there's not going to be any intersections with this geometry. So for this point, you only have one intersected points if you cast a ray, right? Same for these, and same for these. But for these, you have double intersections. So that's kind of a rule that I thought it could be used to determine whether the point is inside the geometry or not. So based on that thought, let's implement that using fx. All right, so going back to the SOP solver, I'm going to add another point wrangle. And in order to reduce the movement of the point, what we could do is to minimize or decrease the weight value, so that if you have a low weight value, that means that the point will start to move really slowly. And when the weight value becomes 0, then the point is no longer movable. So the technique or the method that I'm going to do is to if you have found that the point has a double intersected point, if you cast the ray to both perpendicular directions, then decrease the weight value so that the point is going to move really slowly. Okay, so you still might have going to have some self-intersections at some value, but at least you can reduce it at some point. The point will stop moving. And to do that, I'm going to create a dumper like people do for point-based dynamics. okay, or spring-based dynamics. Right. So first of all, we need to calculate the two intersections to two directions from each point. Right. To do that, I'm going to use a function called intersect. And for the intersect, we need to apply some parameters, geometry, input number, the original point position, the direction to check, and then P is a result, intersected point position result, and the float UV, and also a result for the primitive UV value. Actually, we don't really need a UV value, but still we need to provide it. So let's first create a float U and V in order to store some result value, and then also a vector P1 and P2 to store the result intersected point position. Now we need to do two intersecting calculations. Let's start with first one, intersect. Now the result of this, the output of this intersect function will give you a primitive number of intersected face. So, and if this value is negative, then that means you couldn't find any intersections. So we will use this value in order to determine if the point has been intersected with the primitive or not. Okay, so we're going to check the self-intersection. So we'll do a 0 because there's only one input right here. Okay, and the starting point of the self-intersection will be starting point of intersection calculation will be at P, but if you use a direct at P position, then there's going to be a problem because you're dealing with the self geometry, the geometry itself, and the geometry itself already consists this at P. So that means that so say you have a geometry like this, and this is the P. And if you do an intersection calculation starting from this point, like this arrow already touches this geometry because it is starting from the at P. So in order to ignore the starting point as an intersected point, you have to offset this starting point a bit outward. Okay, so keep that in mind, and the starting point should be a bit outward. I can use the normal direction to offset a point just a bit outside. Maybe multiply with really low value like 0.01 or something. Okay, so this will be the starting point for the intersection. Then you also need to define the direction, which is going to be n. And in order to use the intersect function, you also need to define the length of this ray. And you kind of want to have a really long ray to check if there's going to be any intersect or not. So I'm just going to multiply with 1000 to make it big enough to check, to be able to check really far a distance. If you have like more big geometries, like if the default size is 1000, then you want to make it like 10,000 or something. But for now, the size of the sphere is 1, so using 1000 is good enough, right? And as a result, you'll get P1, U, and V. Right, so that's one intersection going from the point position to outward. Now you also want to check the inward intersection. So let's name this 2, and for this one I'm going to subdivide by, and for starting point just to have a little bit of offset, then also a negative n, which is going to be a inward ray. Right, so if those two value is more than 0, meaning if those two intersect function gives you a result, then that means the point is inside. Oops, sorry. Thank you for the comment. Where was it? So let me start from here. So I was in the sketch view, sorry for that. So in order to use intersect, first of all you need to apply a geometry input number which is equal to 0 right here, and then the original position, the point that you're going to start the intersect from, is going to be at P plus a little bit of offset from the current point position, so you can use at N is the normal direction multiplied by some small value like 0.01. And then you also need to define the length of this. You also need to define the direction as well as the length of the ray. So the direction should be directly at N, which is equal to normal direction. Then also you want to multiply it with a really big number so that it is far enough to intersect with other point on the geometry. Okay. Now, other than that, P1, one thing you might need to consider about is that this setup, this two intersection checking, only works when the geometry is more like a sphere-like shape, or maybe cube or something like that. If it's like a torus shape, it might not going to work, because if you have a torus like this, and if you want to check the points at right here, then if you cast a ray to both direction, both perpendicular direction, you're going to have like 1, 2, 3 intersections, right, like this. So in that case, that might be a problem. This two intersection checking algorithm might not work. But in this case, maybe if you rate at this point position, this direction, you'll have like 2 intersections though. So that might be a condition that could be used as a condition in order to check whether the point is inside a self-intersected point or not. But for now, I'm going to just make it simple, and I'm just going to deal with this sphere-like shape. Alright, so this is one intersection. We're going to create another intersect using naming different using different name, variable name, and then for this one, gonna offset to the other direction, so make it negative n. Alright, so now we have two intersection function, and we're going to determine if the both ray has found an intersect by checking this inter1 and inter2 value, output value from these function. So if those two values are positive, that means you have found that to intersect is to intersect exist for both perpendicular direction. So that means that is the point where you want to stop moving. So that is the point where you want to apply the damper, meaning reduce the value of weight value. So if inter1 is positive, as well as inter2 is also positive, forgot to type 0 right here, then you want to modify this weight, maybe multiply this with a damper value. And this damper value should be smaller than 1, like from 0 to 0.99 or something. So once you found two intersected points, by multiplying a damper value like 0.5, then the weight value will be divided by 2, meaning multiplied by 0.5, meaning the value will get smaller, and also means that the point will start to move really slowly. And if you continue doing that, the weight will get close to 0 and 0 for each time, for each frame, if it is still inside the intersected, self-intersected point. Alright, so apply, and let's promote this damper value, except right here. So I think I want to parameterize this as well, so let's go back to a geometry network, go to the controller, then give a new parameter called damper. The range from 0 to 1. Let's stop by 0.5 to check. Now copy this parameter, then go back to the solver again and paste it right here. Right. Okay, now let's see what it's going to do. I'm going to maybe set the shading to smooth wire shaded, then play it. And as you can see, at some point the geometrical modification has been stopped, and this is due to the damper that we have set. Now if we let's change the damper to 1, meaning there is going to be no weight reduction, and that will give you an infinite like moving, which we don't want. If we set it to 0.9 or 0.8, 0.9, it still reduces the weight value, and at some point the modification will stop. The point moving will stop, like here. And if we colorize the weight value, which I don't able to see right now. Okay, right here. So the red part is the weight value, which is equal to 0, right? Maybe it's better to see in this way. It's a bit too fast. It's a bit hard to see. It might be a bit hard to see, but gradually the red part is increasing. The red range is increasing. Let's set the damper a bit smaller, like 0.5. Okay. You see that the red part is increasing, like here, like this. So this is how you can procedurally create or geometrically create kind of a pseudo-physical simulations. It's not really a physical simulations, but it's pretty close to what we see in the nature. But with custom parameters, you can set yourself to make it unrealistic as well. Okay, so that looks good. Now let's also try to do in the other direction, like a shrinking direction. And how can we do that? First of all, let me also promote one parameter, which is a speed inside this offset primitive point wrangle. This one, I want to parameterize this one as well. So go back to the geometry node, go to the node, controller node, give a speed parameter at somewhere from 0 to 0.5 or something. Maybe that's too big. Oh well. And yeah, let's start by 0.05, then copy this parameter, then go to the solver, paste right here. Now, in order to make a shrinking simulations, let me first try by making this feed to negative to see if it works. Nah, this doesn't work. So that doesn't look good. So in order to make it shrinking, what we're going to do is to just make this speed value to 0, so that we only have this blurring functions, and that makes you a soap-like surface. So the point itself doesn't really move by using any wrangle operations, but we only in this case we only have this blur iterations, and that makes it possible to just make this surface minimal as possible by adding a blur to each time step. If you make it larger, the speed of this shrinking will get faster. And if you have a small number of edges, you're going to see something like this as well. Right, looks good. And if you increase the speed, then it starts to go outward. So you probably could add additional parameter like shrink, toggle that I already showed in the example file to make this speed 0 or not, but it's up to you. In this tutorial, I'm just going to skip that part because it's nothing special. All right, looks good so far. Now, next thing I would like to do, maybe the last step I want to do, is to currently, as you could see, the output geometry from a solver is a bit too jaggy, especially the place where it's close to the constrained edges. Let me increase the speed value to 0.1. You see those edges a bit too jaggy. So let's smooth it out a little bit and finish this tutorial. Hi. Okay, so first of all, I am going to try to use another node after I have calculated this space geometry using a solver. I'm going to create a attribute blur and connect with this one. Now for this attribute blur, I'm going to set the weight attribute as well to weight, and let's set the blurring iteration at some value. Now this will give you a smooth value, but as you can see, the edge that is constrained by the constraint edge, which the weight value is equal to 0, still has some jaggy value. It doesn't become smooth because we're using weight. So to make it even, to make those points which have a 0 weight value to have some kind of, maybe not much, but some kind of smoothness, we would like to reduce or clump the minimum weight value to raise the minimum weight value to something like 0.25 or something, just for the smoothing with this blurring node. To do that, I'm going to give another point wrangle, make it max or min weight. Then just going to modify the weight value by using a mux function, and let's set the one of the value for the max to be a min max parameter that I'm going to set by myself, then also a current weight value like this. So when the value is when this parameter value is 0.2, then if the weight value has a value which is less than 0.2, then all the value will become 0.2, raise up to 0.2 by using this max function. So by doing it, going back to the geometry spreadsheet to the point, the minimum weight value becomes 0.2. So in this case, it is not equal to 0, so some blurring value will be applied using attribute blur, even if you have a weight attribute like this, set attribute like this. So if it's 0, it's like this. If you make it greater, see that slowly, but the edge part is also become smooth. And if you want to apply more smoothness to the edge as well, then you want to increase this minimum value. Then you have more smoothness. Now I'm gonna reduce this to 0.25 for now, and then set the blurring iterations to 5 for now. Okay. Now I think we're pretty much good to go. Maybe I could also add some frame geometry, which is reducing these edges to move. So for that, the edge itself comes from right here, right? So let's make it a null node first. Name this edge. Oops. Constrain edge. Then use something like poly wire to make edge loop. Make it smooth like this, and maybe also color this. I'm gonna color this to black. Okay, now go back, go down. For this one, I also might want to color this. Let's just give a constant color for now, like blue. Then merge them together. Okay, and finally normalize it. Right, so let's see. Starting from this, if you play it, you get a simulation like this. And if you want to show more of these edges, you might want to reduce this value. To make it smooth, you kind of can be able to get the smooth edge, but instead, as a side effect, you'll have this constraint edge being dug into the inside this geometry. So if you also want to show the constraint edge as well, you might want to control these values to suit your needs. For now, I'm gonna just set it to 0.2. Right, or you could also increase the quality of the sphere as well, which makes the simulations a bit slower, but still faster than using DOP, I think. Okay, so that's pretty much it. This is for the inflating, making the speed 0. You can set a minimal, so you can make a minimal surface like this. Now it's already 1 hour, so I think I would like to stop at this point. But just in case, to show that this works for other geometry. I haven't really tried it, so I am not sure if it really works. Let's try it with other geometry like box to make a polygonal mesh and make the axis divisions to a big number like 50, 50, 50, 50. Now that's big enough. Okay, let's see how it goes. And go back to right here. Then set the speed to something like 0.1. Yep, still works, but it's a lot of intersection. Maybe I want to decrease the damper. Yeah, a bit ugly, but make it a bit smaller. Speed. Yep, I like it. Maybe a bit smaller. Yeah, just like a balloon shape. Looks interesting. And that's pretty much it. I hope you find it interesting. Let me also try with torus if it still works, but I don't think it works for torus. But let me try it, because the intersection part have some problem, like I told you. Give some high quality. Okay, now the first constraint edge looks a bit weird. Well, yeah, this doesn't really work. For torus, for things like torus, where you have a more than double intersection for the outward points, maybe you might need to add more additional conditions. Maybe if you have some image how you could do that, you could try that yourself and tell me. Okay. Okay, I think I do have some more time, so I'm going to do a little bit of trying out other kind of constraint edge and finish it, but the tutorial itself is done. So if you let me know if you have any questions about it, and I would like to answer while I'm making other kind of constraints. And let me look at the comments. Okay, thank you very much for all your comments, everybody. Really appreciate it. Yeah, I'm looking at the YouTube comments. I'm also making a live at Facebook and Twitter, but I am not able to see the comment out there, so if you like to communicate, please come to the YouTube. Okay. Please make tutorial about organic growth. Yeah, I would love that. Okay, thank you everybody for the kind comment. Right, so let's also try to make a Voronoi-like shape constraints curve, which is pretty simple to create. I'm gonna use this base, and then to create a Voronoi, you need a scatter point on top of the surface. Maybe this is too much. Reduce this to like 10. Voronoi fracture. The first input is the surface to create a fracture, then second input is point. Then I think you have a Voronoi edges right here. I also need to uncheck this create interior surface so that only the outside surface will be fractured. Right, then next I could use a divide to remove the inner edges and only have the outer edge of this Voronoi cells. Oops. What is happening? Oh. I don't need this second one. Then for the divide, I am going to remove shared edges. Then just retrieve the edge as a curve by using primitive node. Then go to the face hull tab and use unroll with shared points. That will give you a curve like this, and instead of having this intersected curve, I could just replace it with this Voronoi curve. And as a result, okay, I don't see any changes right here. Why is that? Maybe this is too slow. Alright. So if you want to create a grape, this is the way to go. Just have a lot of cell. Then have a small value of blur iterations together with the high value for the speed, which will give you a grape-like shape. And maybe a bit of dumper as well. Nice. Alright, okay, since you want to check the intersection before it happens, can't you check points that are close to intersecting based on the distance? Since you want to check the intersection before it happens, let me check. So I'm checking the intersection right here, right? No, where was it? Yeah, right here. Check intersection, but before it happens, can't you check the points that are close to intersecting based on their distance? Distance and normal. Can't you check the point that are close to intersecting? I'm not sure. I am not sure. I cannot imagine how you could do that based on a normal distance. Probably. Check the intersection point. Can't you check points that are close to intersecting? Well, I'm not sure what you meant by that. If you could show me that with an example, that would be great. From what I tried, this was the things that worked. I have tried using like dot product to use a normal direction, normal vector to check the intersection as well, but that didn't work well. But you might have some more better image doing that, so if you could write it in on a comment, that would be great. Or if you could fork the GitHub repository to create your own files and show that to me, that would be awesome. Yeah. So any other questions? Will you save a record of this stream? Yes, all the stream is going to be saved. You can watch it later on, and you can also download the file from a video description, so don't worry about that, unless I say something really unrespectful for something. I mean that you could check maybe if the normal intersect with a surface that is within a threshold, you could reduce the displacement. Alright, I see what you mean. So by reducing the value right here. Yeah, that might work. That might work, yeah. But you don't, the thing is that you don't know if when checking the other side, you don't know how much the geometry is, how big the geometry is, so it's a bit hard to determine the right distance. So that's kind of a problem, I think. Yeah, let me think about it. Let me think about the best way to deal with this, especially working with a geometry like toruses. That might be a good practice for me for geometrical operations. Okay. I hope you found this interesting, and we'll try to do you can exclude neighbors and check the distance of other points. You can exclude neighbors and check the distance of other points. I'm not sure what you mean by that. I know you could do that, but I don't know how you could use that operations. Well, say you have geometry like this, torus, then if you're looking at this point, or maybe you have another torus, goes like this, and the point where I want to check is right here, right? And sometimes it goes right here as well. Now from here, say you start the ray like this, it goes to this direction as well. For this one, it's like this, just like this. Maybe what I could do is to look for the first intersected points from this point, this one, and for this one, the first intersected points, if we look at it in the zoomed way, because using the distance value is a bit unstable. I think there's going to be a lot of situations the distance value wouldn't matter, I think. So say right here, and then have a ray like this, ray like this. The first intersection from this point perpendicular is this part, and the second one is this part, right? So I gotta see the difference between these points and these points. Now, but currently I don't have, well, the normal direction of the intersected point is facing like this towards this point, but for this point, this normal direction for this intersected point goes to this point, but actually this point goes outside, so there is a bit of difference between these two. So this could be a part that I could use for the condition, maybe, to try that out. I have to try myself using some of my time. So I will do that later on, because if I do it in this live, it's gonna take much more time. So I don't want to take your guys' time just showing you experiments. That's not a good idea, I think. So right, so that's it. If you have any, thank you for the comment though. It's really insightful, and it's really good for me to know what kind of issues there are, so that I can improve the method and also my skill as well. So the comment is always welcome. And okay, so I would like to end the live right here. Thank you very much for listening at this late time. I really appreciate it. If you could join on next week as well, that would be great. I am going to look for other interesting topic that I myself found interesting. Okay, so good night and see you next week. And one thing I forgot to mention, I started doing the series on YouTube called Vex for Algorithmic Design, to show you the basics of Vex, how you can learn the Vex for the procedural design like these. And I'm doing it. I'm going to try to do it weekly. I'm going to try to upload it on Friday at around 8 p.m. in Japan time. So if you're interested, please watch that as well and give some comments. Okay, and you can watch it for free for sure. Right, so that's it. Thank you very much and good night.